joining us to discuss Helium-3, Lunar Resources for Earthly Problems. Please welcome Chief Executive Officer at Interlune, Rob Meyerson. Moderated by Senior Counsel at Pillsbury Winthrop LLP, Sahar Hafeez.
Good afternoon, everybody. I hope you're doing well. My name is Sahar Hafeez. As mentioned, I'm a senior counsel at Pillsbury. My practice focuses on international trade, and I co-lead our minerals practice. I was previously at USTR Commerce and NSC. I know that this is the last session before drinks, and I promise you it's going to be very exciting. We're going to talk about going all the way to the moon and back, and we'll do it all in 25 minutes. I couldn't be more delighted to be here with Rob Meyerson. He's the co-founder and CEO of Interlune and the former president of Blue Origin. He has a deep background in space and engineering. Before we get started, I do want to recognize the leadership of SAFE. This has been a very thoughtful conference that they put together every year, and Abigail Hunter is a true leader in this space, and I just really want to recognize her leadership and the entire team at SAFE, and thank you all for what you do and your leadership in shaping this critical policy area. So in terms of Interlune, Interlune plans to commercialize space resources in the moon and bring it back to Earth, as I mentioned. And they're focused on Helium-3, which, as we'll talk about, is critical for superconducting quantum computers, medical images devices, border security, and fusion energy in the future. This is bold and very exciting. And to do all this, Interlune has support from just about the entire ecosystem of stakeholders, including the US government, labs, private capital, off-takers, all of whom play a critical role in securing our supply chains, as we've talked about at this session. So we will dig into to all of this in this chat. So Rob, before we get started, into Interlune and Helium-3, tell us about what inspired you to co-found Interlune.
Well, thanks, Sahar, and thanks for that introduction. Coming out of Blue Origin, I was really interested in starting my own company. I just didn't really know what. I had decades of experience as an engineer, as an aerodynamicist, and then leading Blue Origin for 15 years, growing teams to do really, really hard things. And I looked around at what's out there. And first thing that I came out with is Blue Origin was one of the pioneers in developing reusable launch vehicles, rockets that actually come back for refurbishment and reuse. And I know that reusability is only going to get you so far. But the cost of access from Earth to space, might get an order of magnitude cost savings. But the next lever for lowering the cost of space missions is to build things in space using resources that you've sourced from space. And that is really what I wanted to focus on in this next chapter of my career is assume reusability is happening. What's out there, out in space, out in the the universe that is priced high enough to warrant going to space and bringing it back to Earth. The other thing that I saw, this thing that I knew was happening, was the Artemis program, which is NASA's program of record for going back to the moon and onto Mars. And that was created in the first Trump administration. And surprise, it was actually continued during the Biden administration. And I say surprise because that was the first time in my career that a NASA program of record had continued across an administration change. And I knew that the interest in going back to the moon was continuing, and certainly, of course, it's continued.
We were onto something.
Yeah, exactly. We're onto something. The moon's important, and people agree. And so those were the two things that caused me to go dig deep into what space resources are out there that are priced high enough, and of course we have a whole conversation to talk about that. Yes.
So now let's get into it. Let's talk about Helium-3. So why is Helium-3 important?
Well, the first thing is it's got all these different uses. Helium-3 is a stable isotope of helium, 2 protons and 1 neutron. It's plentiful in space because it's made naturally in the sun. And so the solar wind has helium-3 and other gases. It's been bombarding the surface of the moon. The moon has been a target for helium-3 for billions of years. Earth has a magnetosphere, so that helium-3 gets deflected away, and we don't get that solar wind on Earth. The helium-3 that we do have on Earth comes from tritium decay. And we make tritium for our nuclear weapons stockpile. It's a controlled material. There's very little of it out there, and it's actually rationed by the Department of Energy isotope program today, and since the mid-2010s. What's it used for? It's used to make things extremely cold. If you want to chill down a superconducting quantum chip to millikelvin temperature and do that continuously, helium-3 is how you do it. There's no other way to do it. It's used on our borders and ports for neutron detection. If you're trying to smuggle a dirty bomb into the country or out of the country, you're going to get caught with helium-3 is what's going to detect that. And in the future, there's been a lot of research in hyperpolarized gas MRI using helium-3 to create some of the most brilliant images of the lung. Fusion energy, there's been research into helium-3 fusion. The challenges with all of these use cases is that helium-3 sells for $20 million a kilogram today, and it has since the mid-2010s. It's so expensive and so rare that there's not a lot of new research being done in it, but there's so much of it on the moon that with these other changes, lower cost launch and the Artemis program, the opportunities to go to the moon, the infrastructure around going to the moon is being built and paid for by others. Mm-hmm. And now this business plan, pencils out. And
and just speaking of the business plan, you also have off-takes, which has been publicly talked about. If you could speak about that a little bit, because that's a key piece of this puzzle here, right?
Absolutely, yeah. So we have announced off-take agreements with two of the leading quantum dilution refrigeration companies. The world leader is Bluefors out of Helsinki, and then Maybell Quantum out of the U.S., out of Denver, have both signed multi-year, 10-year and 7-year off-take agreements that define quantity, delivery year, and price, that commercial market price. We have LOIs for letters of intent for more than $1 billion worth of additional material that we've been working hard to convert to contracts as well. Yeah,
that's very validating, in terms of the whole, for the whole process here. And I know you sort of touched upon this a little bit, that on Earth it's being rationed. Can you speak about why we need to go to the moon for it? You mentioned short supply. What are some of the other considerations there?
Yeah, it's like, why do you need to go to the moon? We've got all the helium-3 we need here on Earth. The challenge is that we don't. The tritium, which is created for our nuclear weapons program, and it's a byproduct of a certain type of heavy water fission reactor. Tritium has a 12.3-year half-life, and it decays to helium-3. We don't make as much tritium as we used to because we don't have as many nuclear weapons as we used to since treaties were put into place, and that's a good thing. There's no current plans to make more tritium. We heard this morning about the challenges in getting nuclear facilities permitted and built. There aren't current plans to expand our tritium production, at least that I've been made aware of, and we talked to the right people. So my guess is it's 10 or more years to deploy and build that capacity, and then you have to wait another 12 years for that tritium to decay to helium-3. So with the growth in superconducting quantum computing, the growth in demand, and no new sources of supply,
So you have a faster runway going to the moon, which is so interesting.
It sounds ridiculous, and 5 years ago it would have been ridiculous. But what we sit down and look at today is that whereas 10 years ago there were 0 companies in the U.S. building lunar landers, today there's 6 major companies, including Blue Origin and SpaceX, all funded, backed by the government, backed by NASA. And we just a few weeks ago had an announcement about a major moon base initiative, which was defined in the president's executive order from last December. That program is off and running. We're going to hear from the program manager tomorrow, but NASA's moving out on getting up to a, 10 to 12 landings on the moon per year starting in 2028. So we're seeing a real acceleration in interest in going back to the moon. And as far as I'm concerned, Interlune and the Helium-3 approach is really the only non-government business plan that really can close on a commercial basis, serving customers like the ones I mentioned here on Earth with these offtake agreements.
So I think many people in the room are probably aware of, kind of the steps that it takes to mine, extract, separate, process on Earth. So walk us through, what does that look like on the moon? Yeah. What are the steps?
So the Helium-3 is implanted in the lunar regolith by the solar wind. It's actually scarring the surface of the regolith, the soil particles, at a microscopic nanoscale kind of level. So what we need to do, and we've identified four steps. One is high volume excavation. We need to process a lot of soil, and we've identified 100 tons per hour. So for those mining people in the room, this is like any given day on Earth. You process that much soil with a single machine. We are working, we have a partner, Vermeer, which is an industry leader, US-based company that's an industry leader in mining equipment. We're working with them on excavation. So that's one area. We built subscale and full-scale prototypes and tested them. The second step is sorting. In any construction site, you need all sizes of materials from fine sand up to gravel of different sizes. We're going to need the same thing on the moon, but what we recognize is that for our downstream processes, we need finer sand, smaller particles. So we've devised a centrifugal gravity agnostic sorting technology that we've developed and flown, and we'll be deploying that on the moon as well. The third step is the actual extraction. Most people have studied heating the regolith up to 1,000 degrees C. That takes a lot of energy. There's no energy utility on the moon. So we have to bring the energy with us. So one of our co-founders is Harrison Schmitt, who is a Apollo 17 astronaut, only geologist to walk on the moon. And we devised an approach that uses mechanical processing those fine particles of regolith I mentioned earlier to separate the implanted solar wind. And it's actually if you look at it under a microscope, it's trapped in bubbles called vesicles. Our theory is that if we process this lightly mechanically, we can do that at about an order of magnitude less energy. And we've tested that on Earth, and we plan to deploy that on the moon in a payload that's planned to go in 2028. The third step is separation, and this is now that you've separated the gas from the soil, you have a mix of helium-3, helium, hydrogen, and other gases. You need to chill that whole stack down to below.
You mean the fourth step, right?
The fourth step.
Yeah, the fourth step. Yeah, got it.
That's separation.
Yes.
We've devised a novel cryogenic distillation approach. We've tested it out in our facility in Seattle, and we're planning to deploy that on the moon, but we're also planning to deploy that on Earth in grade A helium plants on Earth that have trace amounts of helium-3 in them. So we've already devised some partnerships, and what that's going to allow us to do is to start servicing customers we have from these offtake contracts starting in 2028 before we ever get to the moon, and we can start to generate revenues before getting to the moon.
Great.
Yeah.
So we've talked a lot about helium-3, why we need to go to the moon for it, the runway there. So if you talk a little bit about what your plans are to actually go to the moon.
So we have a payload, a multispectral camera that is already packed up and ready to go. It's going to be launched this fall on a mission on a SpaceX rocket with a small rover built by a company called Astrolab. That's going to go to the South Pole. It's going to look at the surface. It's going to measure the age of the soil, the surface, and it's going to measure ilmenite concentration, which is a titanium-rich deposit. Those two things are known to be good proxies for where high concentrations of helium-3 are. And so we've learned that from studying the Apollo landing sites and using remote sensing to determine where the helium-3 might be. Now we're going to land, we're going to measure it up close with high resolution to gather some data. In 2028, or in the fall of 2027, we're going to have a payload that's, about 100 pounds. It's going to have a robotic arm, a mass spectrometer, an imager like the one we're going to send later this year, and then it's going to have 3 devices. One is a heating unit that'll heat up the regolith to 1,000 degrees C, and then 2 other mechanical processing that'll crush it lightly and a little more heavily. And we're going to calibrate our process. We're going to, what we know from the Apollo days is that if you put a sample from the moon in a furnace and heat it up to 1,000 degrees C, you'll boil off all the solar wind gases, the volatiles. If you heat it up to 1,400 degrees C, you'll start to get metals out, like aluminum and titanium. What we're looking for is a lowest energy approach to get most of those volatiles out. And so the mechanical steps that we're taking with this payload are going to get us there. And what that allows us to do is then better build our business case for going to the moon in the early 2030s with an operating plan.
Yeah, so fast, which will be operated out of here. So you'll be sort of, controlling it from Earth, right? Which is so
controlled from Earth, from a control center.
Yeah.
We'll have levels of autonomy on board, of course.
Yeah.
But we'll also have people watching and making sure that.
Yeah. So fascinating.
Yeah.
So just zooming out a bit, can private companies, own what they're harvesting on the moon? And kind of along those lines, what are our competitors and adversaries doing in this space?
Yeah. So no, we can't own the moon. So in the U.S., first off, the Outer Space Treaty, which was signed back in the 1950s, kind of says space is for all of us. Okay. So we have the right to go, signatories of the treaty have the right to go to space, use space for purposes, scientific and other exploration purposes, and also give others the right to use that. So non-interference, non-interference clauses. In 2015, the U.S. signed into law the Space Resources and Utilization Act, which says that any U.S. flag company has the right to go to the moon or any planetary body, harvest resources, own them, and sell them. So you don't own the land you're operating on. There's no claim regime, but there is the right, if the rock is on the surface, it's part of the moon. If you pick it up, you can own it. That's kind of the thinking there. And that was a pretty groundbreaking law. There's other countries that have followed that law as well. Luxembourg is one of the leading countries in space resources. And so we do have, we have some policy and guidance that we can operate under. As far as adversaries and competitors, really we see China as the biggest competitor here. And we talked a lot, and I don't need to explain to this group about the challenges of the past of the rare earth supply chain and losing control of that. We know the Chinese have been to the moon 3 times in the last 6 years. They brought samples back. They published papers on helium-3. And I think, what Interlune wants to be, in a decade is the company that has, sells materials that have been sourced from space to build things and to further the space economy. And we want to do that for all. And I think that if we don't pursue, commercial operations on the moon and do it in a sustainable and thoughtful way, we're going to lose our right to operate, because that non-interference, clause in the Outer Space Treaty can be put to use both ways. It can be helpful and hurtful, and we want to make sure that we're there to operate and take advantage. So.
Yeah, exactly. I mean, just thinking about everybody in this room is aware of, like China has been investing in these supply chains for 40 years. They have a leg up ahead of us. So we don't want to make the same mistake here, especially when there are laws that do create some openings for us, as you're talking about with, where you're actually harvesting, even though there aren't, property rights sort of on the moon per se, as we think about it, the way we think about it here. But there are opportunities, and it's very exciting to see U.S. companies taking advantage of those opportunities and seeing that pathway. So I wanted to kind of, in closing, if you could reflect on, you have just incredible experience in the space industry that, as we've talked about today, you're really bringing to bear here with this project, with your knowledge of that to identify this great opportunity for the country. What in your, vast experience in this industry, what opportunities do you think people are currently not thinking about that are possible or, in this space? Would love to hear your insights.
Yeah, it's, with the lower cost access to space, and so today it costs about $5,000 per kilogram to put something into orbit on a SpaceX rocket. There's some approaches that take a little bit more, some a little bit less. The opportunities that are coming about in the coming years with companies like Blue Origin entering the market, Rocket Lab, Stokes Space Relativity, all building rockets that have some either partial or full reusability. They're going to really compete with SpaceX and bring the cost of access, the price of access down. SpaceX is already disrupting itself with the development of Starship, which is a super heavy rocket that they're building down at Starbase in South Texas. You can realistically see that $5,000 a kilogram coming down to $1,000 and into the mid hundreds or even low hundreds of dollars per kilogram. And that's, when the companies that talk about data centers in space, they need to hit something in the $100 to $200 a kilogram to make these, they've said that publicly, that they need to hit that kind of a price point to make those business plans close. I think anything you've read about in science fiction, growing up over the past, several decades, space-based solar power, space mining, those types of business plans become more realistic as the price of access and the routineness, the availability of access really comes about. That's what makes me so excited about the Artemis program and the moon-based program, because what the NASA administrator, Jared Isaacman, is talking about is over the next 3 to 10 years, creating a construction site on the moon where you're demonstrating, a whole array of technologies. So how Interlune plans to play is not just in the things I mentioned, the payload, the Prospect Moon mission that we intend to fly.
The Helium 3, yeah.
Yeah, the 2028 mission, where we measure Helium-3, but also our excavation technology leads to construction technologies. So going to the moon and demonstrating that we can move regolith to clear and level and compact a site that could be used in the future as a landing pad. The tech that we've been investing in for the last 3 years is applicable to doing that, and there's opportunities to go pursue that and demonstrate that in the next 3 years. So, and anything that I, don't have to go raise private investor capital to go do, makes my job easier. And when my business case and my plans align with NASA's, at least within 20 degrees or so, it's really works out well. So we see this whole moon-based effort as a great way for us to further our program in a non-dilutive way.
So there's a lot of young professionals here, and I was wondering, for those, what advice would you give to them, in terms of to get into this profession, this area? What opportunities are there for them? What's the pathway?
Well, I think there's a lot of, the SpaceX IPO that's coming up this year. There's been a lot of bluster and a lot of talk about it, but the one thing that's for certain is that if SpaceX goes public, it's going to create a whole new group of people who, when they go public, it's going to create a whole new, generational wealth. A lot of tech-savvy engineers and just folks who have worked in the industry, that are passionate about the industry, that may want to start new companies. So I think that there's going to be a lot of opportunities for, as we start to do the things I mentioned earlier, go to the moon and establish a base, develop technologies that can be used to go on to Mars and beyond. It just opens up a whole new group of opportunities. One of those I saw recently was growing food in space. How do you, we're talking about extracting resources from the lunar soil, but how do you grow food, and how do you build out infrastructure like we have on Earth that's just ubiquitous here? You need a permit. Not talking about some of the things we talked about this morning, but building a building, things like that. But on the moon, or in space, something that's in orbit around around the Earth is a whole new ball game, and it's pretty exciting to think about.
It's very exciting, especially as we're looking at competition. We're in an era of competition, and we're looking at how are we ahead of our competitors and adversaries, and this is really one of those untapped opportunities, and we're really grateful for the work you're doing as a pioneer in this space. So thanks so much for your service.
Thank you.
And contributions.
Yeah.
Thank you.
Thanks. Thank you.
Bye.